Right. Good morning, everybody. So far in our econometrics course, we've gone through the first two chapters of the Woolridge Key book. And in these first two chapters of Woolridge, we've talked about what data is mainly and the different types of data, what econometrics is, what we're trying to achieve. And in chapter two, we talked about the simple regression analysis, in which we regressed one independent variable on one dependent variable. Now, in this session and the next couple of sessions that we'll be having, we'll be going through multiple regression analysis. This is going to be chapter 3 of Woolridge's book. So before we start off, let's just discuss what multiple regression analysis is and how it compares to simple linear regression. Uh, so with multiple linear regression, what we're saying is that now, rather than only having one independent variable, we'll be having multiple uh, independent variables. Uh, the beta naught is still going to be the y-intercept, or and the beta ones, beta twos, and these betas are going to be the OLS slopes. Y is still your dependent variable. Mu are all those factors besides x1 to k that might have an effect on y but are considered as unobserved. And we, in the book, we call it the error term as well. So the unobserved component or the error term is mu over here. And we'll be talking about how to estimate this, how to interpret this, and how ultimately this is going to lead us towards establishing causality. Because so far uh, in our simple linear regression, we have left some stuff out, mainly related with how to attain what was called citrus paribus effect. So in this chapter, we'll be talking about that. So before we start off, some parallels with simple linear regression, things that we need to be aware of, which are similar between the simple linear regression and the multiple linear regression. So beta coefficient, beta naught is still the intercept, beta 1 to k are the slope parameters, mu the error term disturbance. We'll still be using those assumptions that we talked about SLR1 to 5, but now since we're talking about multiple regression analysis, we'll be calling them multiple linear regression assumption 1 to 5. So we'll still need the zero conditional mean assumption. Recall when we were talking about the simple linear regression analysis, this zero conditional mean assumption was basically saying that the unobserved component on average, given any value of x1, was zero. But now since we have multiple independent variables, we're saying that the expected value of the unobserved component given any values for x1, x2, x3 is equal to 0. And just like the simple linear regression, in order to come up with beta values, we'll be minimizing the sum of squared residuals. And when we'll be minimizing it, if you recall, in the case of simple linear regression, we came up with two equations, one for beta naught and another for beta uh, 1. With multiple linear regressions, if you have k number of independent variables, that plus 1 beta naught is the total number of first order conditions that you will be deriving in order when you're in the process of minimizing the sum of square residuals. And that those equations are going to be used in to calculate the value of beta, the multiple betas that we'll end up with having. So now, interpreting simple linear regression is another challenge. We haven't talked about this in a lot of detail. In this session, we'll be discussing what this means, um, and I think it's best if we shift to uh, the the note when so that we can discuss this in more detail. But just before I start off with my own notes, I just want to go through the slides till the slide that we will be covering in today's session. I'll give you a brief overview in the beginning, and then we'll talk about it again so that you can kind of understand it when we talk about this again. So this original equation, y hat is equal to beta naught plus beta 1 hat x plus beta 2 hat x plus any amount of independent variables you have, beta k hat into xk. This is the equation or the model that you estimate using data, and this is what you get. Um, Recall that this equation was the equation of that straight line in the case of simple linear regression. In the case of multiple independent variables, it's obviously not uh, a straight line, um, but and a little more complicated than that. But the interpretation is kind of similar to that of the simple linear regression. What we're trying to say is that the total change in the predicted value of the model is equal to the change in the value of x1 times beta 1 plus the change in the value of x2 times beta 2 plus the change in the value of xk times beta k. So this beta has to be, it's a little misleading, it needs to be outside this change sign. The change is referring to the change in value of x times the beta is going to give you the change in the value of y. And in this multiple linear regression analysis, what we'll be assuming is that if you assume that changes in x2 to xk are constant, there is no change. If you assume these values to be constant or you hold them fixed, this would ultimately mean that the change in y would be basically the change in x times the value of the coefficient of x, which is beta 1 hat that you've estimated. And this is how we'll be using non-experimental data to uh, have the citrus paribus or experiment-like effect. And this is the reason why multiple linear regression is such a important or widely used phenomena in research. Then we'll talk about how when we talk about this partial or citrus paribus effect of beta 1 on y hat, we'll talk about it from a different angle, and this we leave to afterwards. After that, we'll talk about how uh, when when you run a simple linear regression versus a multiple regression, the betas of the same independent variable may or may not be the same, and there are some conditions in when the beta coefficients of these the simple and the multiple are the same. We'll talk about that, and we'll talk about how not including all of the independent variables in the estimation results in some kind of bias. We'll talk about what goodness of fit is. This is, if you recall, R square, and in today's session, I'll introduce you to a different kind of R square, which is related with the correlation of your predicted value and your actual value of y. And we'll talk about a couple of examples, and we'll end the session of today by discussing different types of assumptions related to the unbiasedness of these beta estimators. Recall, we've already discussed them. We've already talked about how, in order for our beta 1 to be unbiased, there are four assumptions that need to be fulfilled. The model has to be linear in parameter. The sample needs to be randomly collected, and then the more important assumption over here is the zero conditional mean expectation, when we're saying that the unobserved component in the population is uncorrelated with the independent variables, not correlated with independent variables, or the expected value of the error term given all these independent variables is equal to 0. And finally, the last one was that there has to be variance in the values of the independent variables, and any one independent variable cannot be a constant. With that, let's just go back into failing to meet this criteria would obviously result in what's called biasness in the value of the beta estimators. So let's just start off by, so this is what we have planned for the day. We won't be going through the whole chapter today because it might get too much for you guys to handle. So we'll cover half this time and half in the next extra class that we have planned for next Saturday. Right. So let's just start off. And I wrote a couple of things down that I wanted to stress with you guys during the session. So we'll be starting off from there and we'll see how things go and where we end up with. So, so with multiple linear regression, uh, we want to explicitly control factors that affect the that affect the dependent variable. Um, Let me just copy this and right. So with multiple linear analysis, linear regression analysis, what we're trying to do is, so far in our analysis, what we were doing was we had this y is equal to beta naught plus beta 1 x plus mu, and this was I, and this was I, and this was I. And we were saying that everything else besides x that might be impacting y, we included in the error term. And that is how we came up with the simple linear regression model. Now what we'll be doing is, let's just talk about this one example that you've already seen. We've been discussing this example about earnings, I plus beta naught plus beta 1, education plus the error term. This is the example that we've talked about. Now what we're saying is that there is another component besides education that might impact earning, and let's assume that that thing is a person's IQ. So till in the simple linear regression model, what we'd done was we'd assumed that IQ was something that was unobservable, and we'd kept it in the uh, error term or the disturbance term. Now with multiple linear regression, we'll explicitly control for that factor. And we'll say our model, although we're interested in the effect of education on earning, but in our modeling, what we'll do is we'll have a model that looks like earning I is equal to beta naught plus beta 1 education, excuse the crow, not the crow, the rooster, plus beta 2 IQ and the error term. So we'll explicitly control for IQ as well. And then we'll talk about how education has an impact on earning and how IQ has an effect on earning. And in the process, what we're doing is we'll be assuming that assuming this IQ as being constant. If IQ is fixed, then we'll study the effect of a change in the independent variable on the change on the dependent variable. How does the change in education impact earning if we keep IQ to be constant? And that's the ceteris paribus effect that we're looking for. And that is how we'll be establishing causality. Recall how these two could be correlated, and recall how in our first session that we talked about how correlation is not causation. With causation, you have to control for all of the other factors and then try to establish causality. That's only when you can establish causality with certainty. We'll try to infer causality by controlling some of the other factors that impact earnings. So that's what the plan for the day is. So over here, what I've started off with is an example in which I want to study the impact of education and experience on a person's wage. Recall when we were assuming the simple linear regression case, we were of this opinion that IQ was part of the unobserved component, and we had explicitly assumed that that uh, the that the independent variable. So when we assume Q to be the same irrespective of education in this case, or, and then we assumed it to be zero. What we were saying was that education and mu were not related with us. They would not be correlated with us. Now, this is a big assumption because we've included IQ into the mu over here, and now we're saying that mu and education or IQ and education are not correlated. If they are correlated, then the simple linear regression result recall is only unbiased when this holds. But if it doesn't hold, then your beta one is unbiased. Sorry, it's biased. It's not unbiased. So in that case, what we're saying is, now what we've done is we've taken the IQ out of the mu, because and then this assumption might we're in a better position to say that mu is now not correlated with education, because we fear that IQ and education might be correlated, and they will be. I would like to imagine. So if so I just want to recap over here. If you have something in the mu that is correlated with education, then your beta one is biased. So that's why with multiple linear regression, what you do is you control for all of these factors that were previously included in the unobserved component. Now you take it out explicitly, and now this means that now the chances of the betas being unbiased are more, because IQ you controlled as something that is not part of the error term or the unobserved component. Right. So once we establish that, uh, so we don't need to assume that education and experience, or in this case, education and IQ, were correlated, are uncorrelated. So now education and experience, or education or IQ in the example that I just gave you earlier, can be correlated. Not highly correlated, but they can be correlated. And thus the point being that if you had not put experience into the model and they were correlated, and then it would have been part of the error term, and therefore the error term would have been correlated with the independent variable. Therefore this assumption would not have held, and therefore your beta one would have been biased. Right. So with that being said, let's get back to the multiple linear regression again. So the multiple linear regression looks like this form where you have y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus an error term. And then you have subscripts over here as well. You have yi, and then xi, and x2i, and ui. So that's where you can get data for an individual. And then what we're assuming in the case of multiple linear regression is that the error term, this mu, is not correlated with, is uncorrelated with the independent variables. And we've already discussed about what happens if you add x2, into the, if you don't model it, then you have biased betas. So The next thing that we want to talk about is the mechanics of how beta are calculated. Recall in the case of the simple linear regression, betas were calculated through this process in which we would be minimizing the sum of squared residuals, and this was basically y minus the predicted value of y. So this was what our model was saying, and this is what was the actual data, and we were squaring that, and we were trying to minimize this. And now your predicted model is different because now you have multiple independent variables in the mix. So you end up with the same kind of minimization problem that minimizes y minus, you should put a bracket over here. So I've written it over here, beta naught plus beta 1 plus beta 3 plus the other term. So it's the same process depending on how many independent variables you have. In this case, I have three independent variables, so my k is 3. So once you have this, if you recall, we would differentiate this based on each of these values. So you'd end up with 3 plus 1 k plus 1. K is the number of independent variables plus 1 because we have beta naught as well. You'd end up with these many first order condition equations, and then you'd have to use some fancy maths that you learned in your stats and maths class, in which you would solve a system of equations. You'd have multiple equations in which you'd have multiple x1, x2, x3 is equal to something, then you have x1, x2, x3. Then you'd have a system of equations, and then you would use some kind of magic to actually solve for the value of x1, x2, and x3. Um, I believe in your undergrad, you are probably taught Frank Budnick's book on maths, and in Frank Budnick, I am not sure what the chapter number is for solving systems of equations, but I'm sure you have some kind of practice doing this kind of maths. The good thing about econometrics is that you won't need to do all of that maths and algebra. Um the software will automatically do it for you. So that's one thing that we don't need to worry about. Right. So you can end up with formulas for beta naught, beta 1, beta 2, beta 3. By the end of this session, I'll give you one example, a different approach to figuring out the value of beta 1, but that's for later on. So bottom line is the mechanics of finding out these betas is the same as that of the simple linear regression, but it's tedious. It involves a lot of equations and solving them simultaneously. Uh, so this is the reason why we started off with the simple linear regression earlier, because it's the same thing. It's less tedious. It's you can actually do it. You'll be doing it in the exam. But the same logic applies. Right now, let's just talk about interpreting the regression. So for interpreting the regressions, I've come up with two examples that I want you to read through. And before we talk about these examples, we're using a case of multiple regressions in which we have two equations. We have beta naught plus beta 1 plus beta 2. So the k in this equation is actually k is actually 2, and and what we want to talk about is that this equation can be transformed into the equation given over here. So so you need to understand that beta naught is a constant. It is the intercept of the whole model. So it's telling you where this if you just were to have a line on the graph, where it be cutting the y-axis. So it's the intercept term, and it has nothing to do with changes. Now, the things that do actually have cause the value of y to change are the values of x1 and x2. Let's take a short break over here and then we continue in 2 minutes. Right, so let's just resume. So what we're saying is that in this whole model, uh, if this had a time subscript, we could have taken a difference of these two different times, uh, uh, two different time periods, and then you would have come up with delta y, which is equal to, since this is a constant, it has no role to play over here. You're left with beta 1 x plus beta 2 change in x2. Now, assuming, so the total change in y, according to us, is attributed to changes in x multiplied by beta 1 plus total changes in x multiplied by beta 2 should give us the complete change that happens in the value of y. If we assume that the value of x does not change, then what we're saying is that assuming x2 is constant, changes in y are equal to changes in x times the beta coefficient. So if x1 changes by 1 unit, y would be changing by that times the beta 1 coefficient. So by assuming x2 to be 0 or constant, we are achieving this partial effect or the ceteris paribus effect. We assume x2 to be 0 and then see how changes in x1 will cause a change in y, and this depends on the value of beta 1. And beta 1 over here in our case is therefore just delta y over delta x as well, x1 as well. Change in y attributed to a change in x1. If you've studied a little bit of differentiation, or better yet, it might be a good idea to see if I can take you to that place in the book where we talk about differentiation. If I can take you to that section where differentiation happens, I'd like to read a couple of lines to you about what differentiation is. Hopefully, I can find it somewhere over here. Nope. This is. So what's interesting about the book is that you can always go back into the appendix, and this book has a really nice appendix. And if you're having trouble with maths, all you need to do is go through this appendix. It should give you enough knowledge about everything that we've been talking about in reference to the summation rules and stuff like that. Just give me a second. Let me just see if I can find the differentiation component. It's probably A4, but yes. So this is the summation. These are the summation rules that we've talked about in the first class, and the linear equation that you studied in your maths already. So we don't need to talk about that. Then 1/4 is probably exponential function, right? So what I would strongly recommend is that people should spend some time reading through this. Um, so this part over here is the crux of what we're talking about over here. So if you differentiate a function with respect to x, it's basically approximately equal to changes in y over change in x. Delta y over delta x is approximately equal to the differential of a particular equation with respect to x. So if you were to talk about this equation that I just showed you over here, if I were to find out what would happen uh, to y if there was a very small change in the value of x, what I'd be doing is I'd be differentiating this equation with respect to x1. So if I differentiate this equation with respect to x1, I'll write it over here somewhere. I'll try to fit it in. So if the differential of y with respect to x1, if you think about it, so this becomes a constant. This does not have x1 in it either. This does not have x1 in it either. So you're left with this term. And when you differentiate it, x raised to power 1 becomes 1, and you're left with beta 1. So beta 1 basically tells you how y changes when there is a very small change in x. And that is the kind of thing that we need to understand so that it will help us in the interpretation of these models. Now let's just talk about this one example from the book. I have two of them in this slide over here so that we can go through them together. So the first example over here talks about college GPA, which is the dependent variable. And then you have two independent variables. This is the high school GPA and the achievement test score. So it's like an admission test score. And it's taken from a sample of 144 students from a large university. Both college and high school GPAs are scale variables 1 to 4. They start from they're a 4-point scale, so you have 0 to 4 CGPA. Now, how do you interpret this model? So first we need to talk about the intercept. So the intercept 1.2 is the predicted college CGPA. So it's the value of y if both x1, x2, which are high school GPAs, and the achievement test score are both set to 0. If this was 0, this was 0, you'd end up with the y intercept. And this is the college GPA score 1.29 that you'd get if the high school GPA was zero and the achievement test was zero. It doesn't make so this since no one who attends college has either a zero high school GPA or a zero in the achievement test. The intercept is not by itself very meaningful. So it's not very meaningful. What's more interesting are the slope intercepts, the high school GPA, and the achievement test score. So let's just talk about this. What do we make out of this? So we said that changes in college GPA are actually equal to 0.453 times the change in high school GPA plus 0.0094 times the change in ACT. And we said that we can assume one to be, so if you want to focus on high school GPA's impact on college GPA, you assume there is no change in the value of the achievement test. So holding ACT fixed, um, what we're saying is an additional point in the high school CGPA is associated. So if high school CGPA increases by one additional point, so it changes by one additional point, increases in this case, it causes a change of 1 times the beta coefficient over here, which is 0.453, is associated with 0.453 of a of so it's associated with an increase of 0.53 points in the college GPA, which is almost half a point. In other words, if we choose two students A and B, and the students have the same ACT score, but the high school GPA of a student A is 1 point higher than the other student, you'd expect that on average from multiple students, you'd find that student A would have a CGPA that's a GPA, college GPA that's 0.4 or half a point greater than that of student B. What is important is written over here. This says nothing about two actual people, but this is our prediction about people in average on average, rather than just than exact two people. It's what we're saying is that on average, if you had multiple people like these, you'd find that the person who had the one extra point in high school CGPA to have a college GPA that was greater than the other ones by half a point. Now, when you're interpreting models, the sign is also important because the sign talks about whether it causes an increase in CGPA or a decrease in CGPA. If the sign was negative, then it would have been saying higher high school, an increase in CGPA would cause the college CGPA to fall. So the sign on the ACT implies that holding high school GPA is fixed, a change in the achievement test score of 10 points, a very large change. The average score of the sample is about 44%. The effect will cause less than 1/10 of a point increase in college GPA. So it's a very small effect, and it suggests that it doesn't explain much of how college GPA changes. So your score in your achievement test or your admission test score does not really impact how your CGPAs change. Later on, we'll talk about statistical inference, but it's a good idea to pause this video over here and just go through this whole reading. And I will not go through the next part. I'll just pause it over here for you. You pause the video over here, go through the whole thing, and then move on to the next example and go through the whole thing again. Let me just zoom in on this so that when you're reading it, you are able to do it. If you are unable to read this from the video, go on to the book, and this is example 3.2 of the book. This example over here talks about log wage rather than wage. Now, when you have a log on the dependent variable, I have given you an assignment in which you were supposed to read this one section from the previous chapter and figure out how the interpretation changes. When you have a log on the dependent variable, this um, equation then gets interpreted in the form of percentage. So so 1 unit increase in education causes log wage to go up by 0.92, or in other words, it translates to uh, a 0.92 into 100 times would give you the percentage change in wages. So the wage would increase by 9.2. Similarly, an additional year of experience would cause the log wage to increase again because of the plus sign by 0.4%. Um, an additional year of tenure would cause your wage to increase by 2.2%, or log wage to increase by 0.022. This is actually 2% in terms of wage. So the last part before we close this session with you is something about the properties of the OLS and about this one example in which we discuss the partialing out of uh, phenomena in the OLS. So I'll just talk about these properties with you over here in the video. And when you are done watching this video and then you come to the class for a bit, we'll talk about how this partialing out phenomena is done. And that I leave for the class. So I'll be stopping this session, this recording over here, and I'll be uploading this for you to watch before actually coming and attending the class. So this means that it is a 45 minutes video. I will give you an hour of time to go through this. And then when you come back, we'll sit down and discuss how to do the OLS partialing out thingy. And I think the only way to understand it is through doing it in Excel. So that's it for this video. I'll see you in the next video.